I'm sharing my screen. Is my screen is visible? Your response?
Yes.
Okay. So today we'll start about this RTL design by using Verilog. Okay. So RTL is nothing but last class we seen. I told you about this RTL design register transfer level. This is nothing but this shows that how the data is transmitting through the registers inside when it is converting into hardware. It is looking like a flops. So how the data is transmitting through the registers, that is nothing but RTL design. Okay. So like I think it will take mainly 1 week or like 8 days of time, and so we'll cover all this design flow, introduction to HDL, abstraction, Verilog basics, hierarchy, structural modeling, data flow modeling, and what are the operators and data types, behavioral modeling, and parameterized module functions and task, system task and functions, compiler data and test bench. We'll cover all these things. Okay. So basically, like last class we see in the ASIC design flow, no, same like that only. Just there is a front end. Okay, the front end VLSI design flow. In the specifications, you like so that RTL flow take the specification of the diagram and represent the hardware in RTL. Okay, it will take the specification in the diagram and will represent this in hardware. Okay, and GDS RTL to GDS flow, there is flow yesterday we discussed. Okay, so take the RTL through various stages of logical and physical design steps, and finally it represents the GDS is nothing but what graphical database system, that is layout. So GDS2, yesterday I told you, no, GDS2 is nothing but graphical database system, that is layout. Okay, GDS2 IC means what? GDS take the so it takes the GDS, prepares make for given GDS and fabricate IC. So basically, like you have different steps from specification to RTL, that is front end, and from RTL to GDS there is a back end, and from GDS to IC there is a fabrication. Okay, so like this it will flow. Okay, this is a basic VLSI design flow. Okay, so VLSI design flow. So what is this HDL? Okay, hardware descriptive language. HDL is nothing but what? Hardware descriptive language. Okay, so whatever in the digital you studied about combination circuits and sequential circuits, that combination circuit and sequential circuits you are what we call you are describing in terms of textual format, in terms of programming is nothing but hardware descriptive language. Okay, so this is HDL. Okay. So yesterday also I told you there are like two languages are there. Those are nothing but software language and HDLs are there. Okay, software languages are nothing but C, C++, Java, okay, Python. So these will only like these will generate. I mean, this will develop the what we call application. Okay, they will develop the application. But HDLs we can generate the hardware by using synthesis. We can generate the netlist. Okay, HDL is nothing but it's a language used to describe a digital system. Okay, this is used to describe a digital system. So HDL represents the hardware of a digital system in textual format, textual form. Okay, so you are representing your digital, that means hardware, in terms of textual form, that is nothing but HDL. Okay, so this Verilog HDL is there, no. So our concentration is only Verilog. Okay, our concentration is not VHDL. Why? Because that is hard to learn, and mostly like they are using in the defense purpose. But this Verilog is wherever you go, like RTL designer, they will write the program in Verilog only. Okay, our concentration is only Verilog. Okay, so that means Verilog language provides the digital designer with a means of describing a digital system at wide range of abstraction. There are some wide range of abstractions are there. Okay, so same time it would provide the access to computer aided designs, CAD tools. Okay, CAD tools are last class I told you like EDA tools, electronic design automation, or we can call as CAD tools also. Okay, so for writing this Verilog code and we need to simulate. We are using different types of CAD tools like we are using Xilinx Vivado, okay, and next we are using Model Sim, okay, and Model Sim and Quasta Sim also we can write the program. But Quasta Sim mostly we are using for SV and UVM and Synopsys VCS tools, okay, VCS tools and Cadence tools, cadence so cadence Exilium tools, okay. So these tools will provide the, so by using these tools we can write the Verilog code. Mostly I will show you the Xilinx Vivado, how to write the code and how to write the testament and how to get the hardware, okay. So, what is the job of VLSI engineer? That is, they need to design an IC with meets the required functionality with best quality of result. Okay, in terms of what I told you in the last class, no, that those are nothing but ATP. ATP is nothing but what, area, power, and area, time, and power. So that means it should be like take low area, high performance means low power and high performance. So it should be very fast, okay, and low power, okay, it will take low power consumption at low cost, okay. So this is a job of our VLSI engineer, okay. So HDL, this hardware descriptive language, this will serve as a platform for tool like design entry, verification, synthesis, analysis, okay, enabling the efficient and reliable digital circuit development. So that means HDL, first whoever the RTL design engineer is there, he will take the input from the specification and he will what we call, he will design your whatever the IC, whatever the chip is there, that IC you are designing in terms of RTL code, okay, that is RTL design, okay. So this is about Verilog HDL, okay. And coming to the features of HDL, what are the features of HDL means, so many features of a so it has many features of programming language, okay. I told you, no, so like Verilog, so Verilog, it will support C syntax. It will support which syntax? C syntax. So it have the same programming languages such as C or C++. So you are comfortable with C or C++, understanding Verilog is easy, okay. Additional features are also there, okay. So additional features, and this will describe the characteristics of design with respect to what, here time, okay. So we are talking about simulation time. Here we are talking about simulation time. So with respect to time, it will describe the characteristics. And next one is concurrency, okay. So normal software language is a sequential language. What is sequential language? One after the other, the program will be executed serially. The program, one instruction is executed, after that next instruction, so after completing this instruction, next instruction will be executed, okay. And after completing the next instruction, this is serial, okay, serial in nature, or we can call it sequential. But this is concurrency. Concurrency is nothing but what, parallelly it will execute, okay. So computation can be done in parallel in the hardware, okay. And HDL supports some syntax and semantics, okay. So it consists of some syntax and semantics to distinguish how the parallel and sequential operations are there, okay. So by using some syntax and semantics, we can distinguish, or we can differentiate so how it is operating in parallelly, how it is operating in sequentially, like that, okay. So that means this is the main feature of this HDL, okay. So feature of HDL is this concurrency. So concurrency means what, it is executes parallelly, okay, it will execute parallelly, okay. These are the features of HDL, okay. So like basically abstraction levels are there. Abstraction levels means in digital also we already discussed, suppose the low level is transistor level, and next is gate level, and next module means what, we can define in terms of what we call combinational and sequential, combinational, sequential. Okay, next system level. Okay, so there are two types of levels are there, like bottom up approach. This is nothing but bottom up approach. Bottom up approach. Okay, and next one is top down approach. Next one is top down approach. Okay, so bottom up approach means what? So normally we will design with transistor level, that is CMOS we already discussed. Okay, next gate. Okay, and next is different types of CMOS collected, we will implement gate, either it may be NAND gate or NOR gate, and next with the help of the NAND gate and NOR gate we will implement combinational and sequential circuits, and with the help of this combinational and sequential circuit we will implement the system. That means system means microprocessor or microcontroller. Okay, this is bottom up approach. Top down approach means what? First we will design system, and next we will design module, and next we will design we will divide into different sub modules. Okay, gate and circuit, like that. Okay, this is nothing but top down approach. Okay, suppose if you want to design a ripple carry adder, RCA. Okay, so RCA means first this is RCA. Again this will be designed by using 4 full adders. 4 full adders are designed with what? NAND gates, and NAND gates are designed with CMOS circuits. Okay, so this is nothing but hierarchy. We can say that hierarchy. We are dividing whatever the complex circuits into like different sub modules. Okay, different sub modules. Okay, so that means so abstraction level refers to hierarchical organization of design elements. Abstraction refers to process of representing the digital system in a certain level of details without exposing underlying the implementation of details. Okay, so Verilog support different level of abstractions. Okay, so mainly like we can call this as abstraction levels in Verilog, or we can call as design styles. Okay, so design styles. Okay, how it is operating. Okay, so if you see so there are like 4 level of modeling styles are there. So one is circuit level, next gate level, data flow level, and behavioral level. Okay, and one more level also there, hybrid level, hybrid modeling. These are modeling styles, we can call as modeling styles. Okay, different modeling styles. So that means hybrid level means data flow and behavioral both will write along, so combinedly we call as hybrid level. Okay, so that means lowest level is basically resistor, like resistor, transistor, and highest level is system like CPU. Okay, so we'll discuss all those things. What is the circuit level, gate level? So I told you, last class I told you, like RTL is nothing but register transfer level. So mainly we will represent RTL in data flow level and behavioral level. Okay, data flow level and behavior level. Only if we write the program in this only, we are writing that as a RTL code. Okay, so other than this we are not telling that that is the RTL code. That is Verilog code only. Okay, that is not synthesizable. We can't convert that code into hardware. Okay, so this is the abstraction level. Till here is it fine? Hope you in BTech you studied Verilog, no? Your response, anyone? Hello?
Yes, sir, understood.
Understood. Okay, one second. Yeah. Yeah. So, what about others? Should I move forward?
Yes, sir.
Next you see.
Yes,
So
sir.
here I told you, like there are circuit level modeling, gate level modeling, and data flow modeling. Okay, behavioral modeling. Okay, so here so HDL can be described in the transistor level. Transistor level means what? In terms of CMOS circuits. Transistor level is nothing but in terms of CMOS circuits and modeling as wires, components in the detail. That is a low level approach. Okay, so low level approach, and this is rarely used. Why? Because if you take some complex circuits, so many transistors are required. Okay, so mostly this switch level modeling we are not preferring. Okay, we are not preferring this switch level modeling. Why? Because if you are if you are designing any SOC, or if you are designing any IP or processor, microprocessor, okay, so many, it will be the program becomes very complex. Okay, so you can't use this switch level modeling. Okay, switch level modeling. Okay, and next there is a gate level modeling. Gate level modeling is nothing but you are representing your system by using some logic gates and flip flops. Okay, it describes some interconnection between the basic logic gates to implement the desired functionality. Okay, this we'll discuss, don't worry. So we'll discuss the gate level modeling and switch level modeling in detail. And RTL, so RTL is nothing but I told you, so this is a higher level of abstraction. This shows how the data is transmitting through the registers. Okay, so this is nothing but, that's why we call it the RTL. Okay, so don't confuse with our registers in the digital. Okay, so registers is nothing but inside when you convert your hardware, your HDL code into hardware, inside so many flops will be there, and it shows that how the data is transmitting through the to different types of flops. That is nothing but hardware. Okay, this provides the higher level of abstraction. Okay, so this is closer to the actual hardware implementation. Okay, so by using RTL only we can convert our HDL into hardware, your HDL into hardware. Okay, so that means whenever you want to convert your HDL into hardware, you need to write which code, means RTL code. RTL code. Okay, so that too you need to write in two modeling styles. Those are data flow modeling and behavioral modeling. So data flow modeling means you need to use the continuous assignment statement. This is continuous assignment statement. You need to use assign. Okay, you need to use assign. Suppose these will be expressed in terms of what, means expressions. Okay, suppose half adder is there. Half adder you already studied. What is sum equal to that is a XR B, no, sum equal to A XR B, and carry equal to what, A and B. Okay, carry equal to AB. Okay, so how you write, so that is you need to use a keyword called assign sum. So that means S equal to what, A XR B. Okay, so this is nothing but bitwise XOR operation. Bitwise XOR operation, we'll discuss about these operators, don't worry. Bitwise XOR operator. And next assign C equal to what, this is A and B. A and B is nothing but bitwise AND operator. Bitwise AND operator. Okay, so that means you need to use a continuous assignment statement. This is a keyword. Okay, so like that Verilog, you have you Google it, or you can see in the any AI model, keywords in Verilog. So keywords in Verilog means so many keywords are available. Okay, so this is one keyword. Okay, suppose in just I will Google it. So what are the keywords in Verilog? Okay, just type this keywords in Verilog HDL. Okay, so many keywords you will get. Okay, so here you see FPGA code in. So you can see, so these many keywords are there. Always so always latch, case, end primitive, enum, function, input, logic, output, primitive, repeat, time, while, assign, else, end function. So if, case, else, always, forever. Okay, and end module. Okay, module, local param, initial, reg, wire. Okay, var, wand, passage, negate, type def. So all these are nothing but so many keywords are there. So these are we are going to use in your HDL modeling. Okay, so next, behavioral modeling means you know the behavior of the circuit. Suppose like half adder is there. Half adder means it will do what, A, B, and this is nothing but sum and carry. So just it will I know the behavior of the circuit. What is the half adder? So half adder After will add these two elements. After they will add these two elements, and it will give sum and carry. Okay, I will not bother about the internal circuit. Okay, I will not bother about this internal circuit. So I only write I will write the behavioral modeling. Okay, so that is behavior of the circuit. What is the behavior of the circuit? Okay, like full adder or register. Okay, or flip-flops, what is the behavior of the circuit? Okay, so it consists of different types of like procedural blocks, procedural statements, and procedural assignments. Okay, so what are procedural blocks? Procedural blocks are nothing but it can be executed sequentially or it can be executed concurrently. So there are nothing but initial block and always block. Okay, so we need to write the behavioral modeling by using these two blocks. Okay, initial block and always block. Initial block means it will be executed only one time. Okay, it is non-synthesizable. Non-synthesizable means what? It can't be, we can't convert this one into hardware. Okay, always block is synthesizable. Always block is synthesizable. And what is the name of this always? Mainly always means forever or infinite. Means always means what? Infinitely it will execute. Okay, infinitely it will execute. That is always. Okay, and procedural statements means these are executed within the procedural blocks. So you need to write within the procedural blocks, that is initial and always, and in this you need to execute this. I think in C language you studied if, case, for, or while. These are nothing but procedural statements. Okay, procedural statements. And procedural assignments are nothing but blocking and non-blocking assignments. Blocking assignments are nothing but suppose blocking assignment means suppose y equal to, let us take a and b. Okay, and y equal to some a or b is there. Okay, so here this instruction is executing. Okay, this instruction will be in blocked state. That is nothing but blocking assignment. Okay, so when this instruction is executing, this instruction will be blocked state. So this will execute sequentially. This will execute sequentially. Non-blocking means what? Basically for the combinational circuits we will use blocking assignments. Okay, combinational circuits we will use blocking assignments, and for sequential circuits we will use non-blocking. So non-blocking means what? Non-blocking means this will execute parallelly. This will execute parallelly or concurrently. It will execute. Mainly for the sequential circuits, we'll use this non-blocking assignments. Okay. So this is about the blocking and non-blocking assignments. Okay. So basically in the behavioral modeling we'll use the procedural blocks, that is initial and always, and procedural statements, those are nothing but if, case, for, while statements, and we'll use the procedural assignments, those are nothing but blocking and non-blocking assignments. Okay, did you understood? Shall I move forward?
Sorry, sir, where we use blocking?
What?
Where we are using the blocking
Blocking
assignments?
assignments mainly for the designing of combinational circuits. We'll use these blocking assignments. You have a combinational circuits, no? In the digital, you have a combinational circuit. For writing the program in the combinational circuit, we will use blocking assignments, and for sequential circuits, we will use non-blocking assignments.
Okay.
Okay, yeah.
Okay. So this assign is equal to b plus c is a. Okay, this is not a procedural. Okay, fine,
Okay,
thanks.
yeah. So one condition is there are port rule connections are there. That port rule connections output, when you are using behavioral modeling, output should be reg data type. That data type we will discuss. Okay, output should be reg data type. We need to initialize. Okay, when you are using continuous assignment statements, all output and input can be by data type. Okay, that data types we will discuss. Don't worry. Okay, yeah, yes. So basically how the structure will be there, that means module is a building block of any Verilog code. Module is a building block of any Verilog design. Okay, so it will start with the module and end with end module. Okay, so next next module name. Okay, this is nothing but module name, or we can call as identifier. we can call as identifier, module name or identifier. Okay, and here you have port list and declares. Okay, declaration will come, module items will come, like that, and end module. Okay, so I told you, module name is nothing but this is identifier that uniquely names the name of the module. Okay, suppose if you are writing for half adder, how to write module, you can write HA. HA is nothing but identifier. Okay, so you can initialize input A comma B, and output so output sum comma carry, like that. Like this you need to initialize. Okay, and port list declaration. Okay, port list declaration means there are two styles are there. Suppose one style is so module half adder. Okay, here you initialize the variables A, B, sum comma carry, and here separately you need to declare input A comma B and output sum comma carry. Okay, output sum comma carry. So like this you can declare separately. This is style 1. Okay, and style 2 is within the bracket itself you can declare the inputs and outputs. Okay, so module half adder, this is my identifier and module name, and input, what is my input? A comma B comma output S comma C. So like this I will declare. Okay, so that is nothing but this will declare the input and output ports. Okay, that wherever you are using in the design, and this is nothing but declaration. Okay, the declaration of your variables. Okay, so whether you declare your variables with data types, we are using reg data type or net data type, like that. Okay, suppose if you are using functions or task, there you need to declare the functions and tasks, like that. Okay, and module item means you need to write the procedural blocks. Those are nothing but you need to write your module items within this initial construct or always construct. Okay, or we can use continuous assignment also. We can use, so continuous assignment statements also you can write. Okay, so you can use, suppose if it is a behavioral modeling, so you need to use the procedural blocks like initial or always, or if you are using data flow modeling, you can use continuous assignment statements also. Okay, so those we are declaring in the module item. Okay, module items. This is the basic my program structure. Okay, program structure will be there. Okay, and if you take the circuit level modeling, this is nothing but basic circuit level modeling. We already seen the CMOS circuit. No, CMOS circuit, you have pull up network as PMOS and pull down network as NMOS. Okay, this is a 4-terminal device. Body is connected to source. Okay, here body is connected to source. So like this is the syntax. NMOS instance name. What is the instance name? Okay, NMOS, and what is my instance name? We need to use the instance name, output, data, and control. Okay, suppose if it is NMOS, what is the instance name? Let us take, this is N1 and this is my N2. Okay, so instance name N1, and what are the inputs are there? Drain, source, gate. Okay, so here you see, so module, this is my inverter. No, this is my inverter. So this is basically we are not using, just for the idea purpose I am telling. Okay, so inverter, so module, what is my identifier? Okay, before this, one second. Yeah, lexical tokens are there. Okay, one. So see here, so module inverter underscore gate, this is my identifier. And what are these? This is style 1. Okay, style 1, I told you, no, style 1 means what? So we are representing the variables inside the bracket, and separately I mean initializing the inputs and outputs. Okay, so what is input? V in is nothing but my input, output is V out. Supply 1 is VDD, and supply 0 is ground. Okay, so how to instantiate, that means how to write the code, that is my instance. So this is PMOS, and instance name is optional only. So output, what is the output? V output, and next data. Data means what? For PMOS, what is data? VDD, and input V in. Okay, and NMOS, V out. Okay, this is V out. First output will come. Output, next data, that is nothing but ground. For this NMOS, what are connected? Input, output, and ground. No? So ground and V in and N module. Like this, we will write the switch level module. Did you understood? Shall I move forward?
Yes, sir.
Okay. Next you see gate level modeling. In the gate level modeling, you are using gate level primitives. What are the gate level primitives? So gate level modeling that are ready to be instantiated. So that is so Verilog have built-in primitives. What are the built-in primitives? AND, OR, NAND, NOT, NAND, NOR, XOR, XNOR, buff if 1, buff if 0. Like that, these are the gate level primitives. Okay, the syntax will be like this: primitive underscore name, primitive name. This is my instance name. What is this? Instance name. Output followed by inputs. Okay, so let us take one example. This is nothing but my half adder. Okay, so half adder, how I can write? So module half HA underscore gate 1. This is module name is what? Or my identifier name. Identifier is nothing but HA underscore gate 1. Output sum comma carry, input A comma B. This is style 2. So I can declare the inputs and outputs within the bracket itself. Okay, so sum comma carry, input A comma B. So I am using gate level primitive. XOR output. What is my output? Sum comma A comma B, and input and carry comma A comma B, end module. Okay, like this I can write. Okay, one more style means XOR my instance name. What is my instance name? This is G1 I can consider. This is G2 I can consider. Okay, so instance name. What is my instance name? G1 sum comma A comma B, G2 carry comma A comma B. Like this I can write the code. Okay, so this is nothing but gate level modeling. Okay, gate level primitives or gate level modeling. Okay, and yeah, suppose data flow modeling is not there. Okay, one second. Yeah, if it is a data flow modeling, how I can write means here same for half adder. So how I write? So module. What is my module name? HA underscore gate. Okay, what is output? Sum comma carry, input A comma B, sum comma carry, input A comma B, and here I will use continuous assignment statement. What is the continuous assignment statement? Assign S equal sum equal to what? Sum equal to A XOR B. Okay, next I will use assign carry. Okay, so what is my carry? Carry equal to A. This is bit level operator. Okay, bit level XOR and bit level AND operator, and end module. Okay, so this is my gate data flow module. Okay, here I will write data flow modeling for both simple half adder. Okay, so this is half adder, and next RTL, register transfer level means yeah, here data flow modeling is there. So in the RTL we need to use which flow modeling? That is data flow modeling and behavioral modeling. So RTL modeling is synthesizable code style. Synthesizable code style means what? We can convert into hardware. That is synthesizable module. Okay, so we'll use data flow modeling and behavioral modeling. Same half adder code I took. Okay, so module. So what is my module name? Half adder HA underscore data flow, and inputs are A comma B, sum comma carry, and inputs I need to declare. Okay, this is style 2. that is your wish. This is style 1. Okay, so which style you are following, that is your wish. Okay, basically you go for style 1, style 2 only. That means better to represent your inputs and outputs within the bracket only. So input a comma b, output sum comma carry. Okay, output sum comma carry, and assign. Okay, like in data types, I'll tell you the data types. Data types, you have two types of data types are there. Okay, data types is nothing but how we are storing the variable into the computer is nothing but data type. So mostly, like mainly we are using net data type and variable data type. Variable. Okay, variable data type. In net data type you have var and wand. Var and wand. Okay, so like this net data type will not store any value, just we can drive the value, that is nothing but net data type. Okay, variable data type means reg data type. Okay, reg data type means we can store the value. Okay, so like here you are initializing a comma b, no, by default which data type you are using means y data type. Okay, when you are not declaring this y data type, by default the compiler will take as which data type means y data type. Okay, just you keep in mind. Output sum comma carry. Okay, sum and carry is also y data type. I need to use a keyword called assign. Assign sum equal to a XOR b, assign carry equal to a and b, and end module. This is nothing but basic my data flow modeling. Okay, and behavioral modeling means here you see behavioral modeling. So module and this is my identifier, half underscore behavioral modeling, input a comma b, output. So if you are using behavioral modeling, output should be reg data type. Okay, output should be what data type? Reg data type. Okay, so reg data type. So I am declaring reg sum comma carry. Always I need to use the procedural block now. So initial block is non-synthesizable. So non-synthesizable initial block where you are using means in the test bench we are using. Okay, so in the design we can't use the initial block. Okay, so in the test bench we can simulate, that's why initial block we are using in the test bench, but in the design we can use always block, always at the rate a comma b. This is nothing but sensitivity list. This is nothing but what? Sensitivity list. Okay, sensitivity list means if there any change in the inputs, there is a change in the outputs. Okay, if there any change in these inputs. Okay, so suppose like your design have some 100 or 150 inputs are there. Okay, so every time you can't declare the sensitivity list in the bracket, no. So in that situation you can write always at the rate star, always at the rate star. So this is nothing but implication operator. This is nothing but implication operator. Implication operator means any number of inputs are there. If there any change in that input, there is a change in the output. Okay, 100 inputs are there, 150 or 1000 inputs are there. Simply if you keep star means what? That will be applicable for all the inputs. Okay, so begin, and I am using case statements, switch statements. Okay, I told you, no, we can use the procedural statements. Those are nothing but if. So you can use in the behavioral modeling, you can use if, case, for or while statements you can use. Okay, here I am using case statement. Okay, so case, so that means you know the truth table for half adder. So this is a, b, and output is sum and carry. Okay, so this is 0 0 0 1 1 0 1 1. Okay, sum, so 0 sum 0 carry 0, sum 1 carry 0, sum 1 carry 0, sum 0 carry 1, no? Sum 0 carry 1. So based on this truth table only I am writing the case statement. So if it is two tick binary, this will see values at this how we are declaring the binary values we will see. If it is a binary value means this is size, and binary is nothing but b is nothing but that radix, what type of number system you are using. So we already seen the number system now, binary, octal, hexadecimal, and decimal we are seeing, no. So 2 tick binary 0 0. Okay, if it is 2 tick binary 0 0, so begin. So if it is multiple statements, you need to write between the begin and end. Okay, so multiple statements are there, more than 2 statements are there. So that's why I am writing between the begin and end. Sum 0 carry 0. So if it is 0 0, what is the output? Sum 0 carry 0. If it is 0 1, input is 0 1, some 1 carry 0. Okay, if it is 1 0, if it is 1 0, some 1 carry 0. Okay, if it is 1 1, if it is 1 1, okay, some 0 carry 1. Okay, so these are the different styles we are using in the Verilog. Okay, did you understood? Any doubts or any queries in this?
So in behavioral model, sir, so do we get any flip-flop or latch here because we are using reg?
No, no, will not get. Here we are writing for the combinational circuit only.
Okay, means okay, there will not
Suppose
generate.
if you are
Okay.
writing for the flop,
Mm-hmm.
there what you will write means so always suppose if you are writing for asynchronous active low reset means always at
Mm.
right passage of clock or negage of reset you need to write negage of reset.
So latch also will not generate here.
Here latch will not run, just we are writing
Okay.
program for simple half adder.
Okay.
Combinational circuit. This is combinational circuit. Okay.
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 And for the net, what is these two other war and wand?
Over and one means suppose if you take like uh, so suppose you are declaring wire A. Okay. First you
Mm-hmm.
declared suppose assign a equal to 0. After that you assign a equal to 1. Okay, what so if I display, so I'm using system task dollar display the value of a is percentage d comma a. Okay, can you
Mm-hmm.
expect what is the value of a after compiling this?
One.
You are getting a equal to don't care.
Okay.
Why? Because compiler can't understand this is nothing but sequential in nature. First A is assigned to what? Assigned to 0 and A is assigned to 1. Okay. So compiler can't decide whether to store the value 0
Zero
or
and
1.
one.
So it will throw what? X. It will throw X. Okay. So that means here if you use var A means what? It will do OR operation. 0 or 1. What you are getting 1? No? Here you will get A equal to 1.
Okay.
Suppose if you use WAND, here in this you are using 0 and it will do AND operation and 1. You are getting A equal to 0 like this.
Okay.
Is
So
it
is it
clear?
synthesizable or it is just for test bench?
This for testing only. This for testing only.
Okay. Okay.
This is not
Okay. Thank you, sir.
synthesizable. So when it is synthesizable means you need to write either in data flow modeling or behavioral modeling, that is RTL code, then only that is synthesizable. I will show you how it is synthesizable. Just I will show one program.
Mm.
1 second. Mm, yeah, you see here this is these are some Verilog codes. 1 second. Verilog codes. This is level 0. I'm writing for what means half adder data flow modeling. Okay, half adder data flow modeling. Text bench I will tell you afterwards. I will tell you how the tool is giving the hardware. Okay, so this is my simple code I wrote in GVim. GVim is nothing but one powerful editor. So basically so many commands we need to use, and we are using in RTL coding in GVim. This is my code I wrote for the half adder by using data flow modeling. So module, and what is my module name? Half underscore dut, and input a comma b, output sum comma k carry. Okay, I'm using assign sum equal to a x or b, assign carry equal to a and b, and end module. So this code I am going to execute in Xilinx Vivado. So this is one of the EDA tool came from AMD company. Okay, Xilinx Vivado. Previously, I told that Xilinx is one company, but AMD acquired this Xilinx. Okay, so I will try to show this the output in the Xilinx Vivado. So like as a PD engineer, you need to have the idea about how the how this front end people are doing. So what they are doing, you should have the idea. So I'm not going deep into that. Just for idea purpose, I'm telling. Okay. So this is the code I wrote. Okay. This is nothing but whatever the code I explained. Is it visible? No. Yes or no?
Yes, sir.
Okay, so here this is the code whatever I explained. I just you need to save this code. Okay, so you need to save this code, already saved. So here if you see elaborate design, okay, if you elaborate the design, so I want to see the hardware, how it is getting. Elaborate design means here I can see the simulation part also. So we depending on the waveforms, so I will get so for the simulation, getting the simulation, I need to write the test bench. So I'm not going into test bench. After completing some topics, I will explain you the test bench. See here, I got the circuit now. Half adder have XOR gate followed by AND gate. XOR gate followed by AND gate. Okay, and here half adder logic gates. This logic gates also again right. Okay, so logic gates data flow modeling is there. So logic gate. This is a logic gates. One second. This is test bench. This is data flow modeling. Okay, so you know all the gates, all the basic gates. Okay, so just these are the basic gates. So here yeah, you see here so module, and module name is all under all gates A B C Y, and input A comma B, and output this vector concept I will tell you. Suppose multiple inputs are there, we need to declare with this is vector. Okay, 6 down to 0 is nothing but 7 inputs are there. Okay, assign, I need to use a continuous assignment statement. Assign y of 0 equal to A and B, AND gate. Assign y of 1 equal to A or B. Assign y of 2 equal to not of A and B. Okay, these are operators, bitwise operators, I will tell you. So not of A and B, this is NAND gate, and this is not of A or B, NOR gate, and this is inverter. Okay, inverter. Okay, not of B, not of AX or B, this is XNOR, and this is XOR operation. Okay, so this one, this is my module name, no? So just to copy this, and here itself I am doing, where in the Xilinx Vivado. So close this. Here in the design source, just add this design. Okay, so what is my design? Suppose all gates. Okay, all gates is my design name. Finish. It is asking to make this module name is also all gates. Yes, yes. Okay, so I created this all gates, and here this one I am copying this code. Just copy this and paste in this. Okay, paste in this, save this, save this. It is saved. Okay, after that, whatever the design I want to see, so here initially this 3 dots are there, no? So 3 dots are there means this is in top module. Okay, so whatever the design I want to see, so right click, set as top. I need to make set as top. Okay, and next run the elaborated design. Run the elaborated design. Yeah, you got the hardware, no? See here, this is my hardware. Okay, so 2 inputs are there, and how many outputs? 7 outputs are there. So one is coming through the inverter, and other is XOR gate. Okay, and next one is AND gate, and next one is OR gate, XNOR gate also. XNOR gate is this is coming through this one NAND gate, and coming through the inverter NOR gate, and coming through this inverter XNOR gate. So all gates are covered. Okay, so that means here what happens means circuit, based on our program, circuit is converting into hardware. So basically in the digital, what we did, suppose if you design any like half adder or full adder, how you did, first you draw the truth table, and next next you draw the k map, and from the k map you got the logic expression. From the logic expression you draw the logic diagram. This is the process of designing of combinational circuits, no? So here what I am doing means I am writing the program either in data flow modeling or behavioral modeling. So automatically whatever the compiler is there, the compiler is converting your code into hardware. Okay, so this is about today's session. Any doubts or any queries?